Now let's do an example. Let's say can factorial. So the program goes like this: y is 1, b specified with the Hoare triple x greater than or equal to 0 factorial, which is the name of the program again, y equals okay. So let's see how we can do this. So let's take the case where x equals to 3. Okay, in this case, now we have the initial values as y equals 1 and x equals 3. Okay, now y is y into x. So y will be 1 into 3, 3. X is x minus 1, which means 2. In the next case, y is 3 into 2, 6, and x will be 1. And then y will be 6 into 1, 6, and x will be 1 minus 1, 0. So now x is 0, so we come out of the loop and we end the program. So here, as you see, we need an additional variable to capture how the final values of these variables relate to the initial values, because the value of x changes from 2 to 1 to 0. So we need to capture how the initial values of these variables change during the progress of this execution of the program. So what do we do when we are faced with a scenario where there are changing values to a variable? We have to use a new variable to capture the initial values so that the changing values could be captured by the general variable. So what do? We define a new variable into this program called x naught, which will be the initial value of x. So this relates to the initial value of x. And these types of variables which are introduced newly to the program so that it can capture the initial values are called logic variables. Okay, so having said that, how do we write the proper Hoare triple to this particular program called factorial? Is we have x is greater than or equal to 0, just like how they mentioned in the question. We add the initial value of x as a conjunction to this part. And then we have the name of the program, factorial, which will consist the body of the program. And then What do we have next? Y will have the factorial of x, but now it's not x anymore because here we introduced a new variable called x naught to capture the initial value of x. So y will be equal to the factorial of x naught, whereas x will capture these changing values and x naught will capture the initial value of x. So the answer will be the factorial of x naught. So now let's look at the tutorial. The first question says, which of the following Hoare triples are valid? We have true x equals 5, x equals 5. So this is valid. So initially we have true and then the body is x equals 5 and then the post condition is also x equals 5. So it's valid because P is satisfied while S is being executed, and the result of S, the resulting state after the execution of S, is satisfied by Q as well. So this is a valid statement. And then the second one, x is 2, x equals x plus 1, x equals 3. This is also valid. You see, x is 2 initially, so 2 plus 1 is 3. So the result generated by the execution of S is x equals 3, so that's satisfiable as well. Third one, true x equals 5, y equals 0, x equals 5. So again, this is valid. The body says that the value of x is 5, so at the end of the execution Q says x is 5, so it's valid again. Then the next one, x is y if x equals to 0, then x equals y plus 1. Else z equals y plus 1. And the post condition is xy plus 1 or zy plus 1. Okay, so to check this we can use the proof rule for if as well. So let's use that method and see. So we have x equals y. P and C. Then we need S. What is S? X equals y plus 1. And then we need Q. Q is O. Okay, so what I'm doing is I'm applying proof rule for y. Then the next triple, now what we're doing is we're separating the if part and the else part. So the next one is P and negation C. So we have x equals y and negation of x equals 0. And then we have z equals y plus 1. And then finally we have Q. Okay. Now what do? We apply the assignment rule. X equals y plus 1 or z equals y plus 1 e over x x equals e q. Same thing comes here. Next part, O z equals y plus 1 e over x z equals y plus 1, and then that part comes again. Okay, once we have that, we are going to replace x with e. So we have y plus 1 equals y plus 1, or z equals y plus 1. X equals y plus 1, and then that. Next, what do we have? X equals y plus 1, or y plus 1 equals y plus 1, z equals y plus 1, and then q. Same thing. Okay, now here y plus 1 equals y plus 1, that's true. So that we have true there, or we have that. So true or this results in z equals y plus 1. So let's write that. X equals y plus 1, and then what's next one is, again here we have y plus 1 equals y plus 1, that is true. So t or this results in this part. So let's write that. Okay, so as you see, we have this and this as the two separate Hoare triples. So we can notice that the first Hoare triple is correct, is valid rather, because we have this, and then the state that results after the execution of the program is satisfiable, because either this part or this part will be satisfied. And then looking at the second Hoare triple, initially we have this and then we have this, so the state that comes after the execution satisfies either the first part or the second part. So that is valid. So we can say that the question which is given in D is a valid Hoare triple because we get the validity like this. And the rule that we used here was the proof rule for if statement. You can derive the answer just by looking at the Hoare triple given in part D as well, because if x is equal to 0, then what we do is we assign y plus 1 to x. If that's not the case, if x is not equal to 0, then what we do is we assign y plus 1 to z. So in either case, we have x equals y plus 1, or we have z equals y plus 1. So those are the only two answers which are given by this statement. So the final state that results after the execution of this program need to have either x equals y plus 1 or z equals y plus 1. So therefore, this Hoare triple is valid.